All right, so let's talk about homogeneous linear ODEs with constant coefficients. So here we have an nth order homogeneous constant coefficient. So basically we're just doing what we did last time. And so here, so the standard, pretty sure that's not how that's the wrong standard. I think it should be ARD. Whatever, I'll fix the notes later. Don't mind my English. Nth order ODE with constant coefficients as follows. So here we're just going to have an nth order with constant coefficient where AI are just real numbers. So here we just have real numbers here. So the solving problems in chapter 3 is very much like 2, just with higher orders and general solutions. So basically, ta-da, I typed it all up. So here we have distinct real roots. So we have, as long as they're all different, you can just say e to the lambda x's are all different things. And so basically when you do this, you're going to have chunks of solutions, right? You'll see what I mean by that. You're going to have a bunch of distinct real roots. You're going to have multiple real roots. You're going to have simple complex roots. You're going to have multiple complex roots. And you're just going to kind of put it all together in some sort of weird combination. But it's the same thing as it was before. If I have distinct real roots, we just use each one of the distinct real roots as its own solution, where it's e to the lambda x, right? For our if I have complex roots, and hold on, I guess if I was going to do this differently, I switch these two. Now I'm thinking about it. If I have multiple real roots, so if I have a multiple, I'm just going to have one of them be that, and then I'm going to add an x, and then as many of those if I have. So if I have lambda 4 equal to lambda 5 equal to lambda 6, and all this is equal to 11, right? And let's say I have lambda 1 is equal to 2, and lambda 2 is equal to 4, and lambda 3 is equal to minus 7. My solutions is y1 equals e to the 2x, y2 is equal to e to the 4x. My solution here would be y3 is equal to e to the minus 7x. But for here, y4 would equal e to the 11x. And then y5, I'd have to increase, I'd add an x, so x e to the 11x, and then y6 would be x e to, or x squared e to the 11x. And so I just keep going up. So that makes sense. So if I got all these as roots to my characteristic polynomial, if they're distinct, go ahead and just write them out by themselves. If they're multiple real roots, then here I have, then you just go ahead and no matter what lambdas they fall in, just go ahead and add x's for every time you have it repeated. And then for simple roots, we'll have what we had before. So if I only have one set of complex numbers, which are different, right? I'll have e to the cosine x, e to the sine x. But if I have multiples, and so if I have lambda, say let's pretend here I have lambda 4, or what am I even at? I'm at like 7. So let's pretend that lambda 7 and lambda 8 are equal to 2 plus or minus I, and lambda 9 and lambda 10 is equal to 2 plus or minus I. So this complex root appears twice, right? Well, you do the simple root like you did before, and then guess what? You just slap an x on it, as many times as you need to. And so here in this case, we would have lambda 7 equal to e to the a. So here I have it as 2x cosine of, in this case, I'm missing an x, aren't I? There should be little x's in here, shouldn't there be? Unless I'm crazy. There should be x's in all of this. And so it'd be cosine x. 8 would be e to the 2x sine of x, and then y9 would be x e to the 2x cosine x, and y 10 would be x e to the 2x sine x. Okay, and if it was repeated again, I'd have another set of x's. Okay, so just slap on x's if you have repeats up until they're unique. It works out the same. And so, given this, you should be able to handle everything at this point. So this is just an example. So let's go ahead and crunch through actual real examples. All right, so let's look at this thing. So find the general solution. So step one, we're going to write the characteristic equation. So the characteristic equation, that's step one. And in this case, it'll be lambda cubed minus 2 lambda minus lambda plus 2 equal to 0. Step two, solve for lambda. So we're going to solve for the lambdas. All right, so we'll do that. How would I solve this? Well, I'd solve it by grouping, right? Here's a group, and I can solve. I'll just give you what the answers are. Everyone's just going to solve this in a calculator. I can almost guarantee it. I highly doubt anyone's going to say, well, I can pull out a lambda square here, and then this is lambda minus 2, and then I can pull out a negative here, and I'll get lambda minus 2, and then here I'll have lambda squared. No one's going to do that. You guys know how to do it, but you're not going to do it. You're just going to chunk it through whatever calculator is in front of you, which is fine. This is a differential equations class. So here we solve for it. And so here's step 3. Write general solution. And so here our general solution is as follows. So it'd be C1. And so these are all real and distinct. So what do I have here? I have C1 e to the minus x plus C2 e to the x plus C3. That's not a 3. E to the 2x. And that's it. All right, we're going to do the same steps again. We're going to do it for this one. All right, so step one. Write the characteristic equation. So here we'll have lambda 5 plus 3 minus 3 lambda to the 4th minus 3 lambda cubed plus lambda. I said lambda. Did my brain write lambda? No, my brain says, hey, I don't like you. I'm going to make you look like a fool in front of all your students. Okay, let's do that. Does anyone else's brain hate them as much as mine? So here, once we take our characteristic equation, we'll solve it. Can you solve this one? You could, right? It just has a bunch of repeaters. So I'll say lambda 1 equals lambda 2, which is equal to 0. So true from a 0, because pull out an x squared. And then here we'll have lambda 3 equals to lambda 4, which equals to lambda 5. And all of these equals lambda 3, 4, 5, and all those are 1. So it's a bunch of zeros and ones. So here, so step 3, we're going to write out our general solution. And so here we have y1 equals, so e to the 0 is just c1, so it's just a constant, plus c2 x e to the 0, so we just some x, right? And notice how this completely solves this, because if I take its double derivative, these are both 0, right? 0, 0, 0, right? So this covers all my zeros, right? Then we have c3 e to the x plus c4 x e to the x plus c5 x squared e to the x. And does anyone have any questions how I produced any of these? You didn't though, right? No, I didn't.
Good. I do have a question. Just with when you're writing it out with the order of like what you choose to be lambda 1, lambda 2, do you just go like smallest number, like negative to positive?
Yeah, when I do that, I kind of put them in order just for teaching purposes. But if you guys have them in whatever order, it doesn't matter, right? It
Okay.
literally doesn't. So I will not. If your coefficients say 4 and 20 and 10, as long as you still have 5 of them in the right order, I don't care, right? I literally
Okay.
don't care how you label them.
Cool.
I said that one time, and then I had this in one of my students. I had lambda moose. I had lambda rabbit. It was consistent. It was consistent. I was like, I don't care. Oh, the worst thing was like, because I used to say never leave anything blank, because even if you draw a picture of a moose, I don't care. It's worth a point, right? And it's just what I say, right? I don't care what marketing it is, right? And so on one of the skip problems on the final, someone drew this like huge Than moose, right? It was like a moose that was like somewhere between a moose and Thanos, and it had like the big chin and all this other stuff, and like power stones in its like antlers. And I'm like, I gotta give harder exams. You have time to draw all this. I just do. Anyways,
I have a quick question.
go for it.
So with with lambda 1 and lambda 2, those are equal to 0. So when you do the equation and you do C1 and C2, those don't have e to the x's because e to the 0 is 1.
Yeah, so e
But
to the 0x is just.
yeah, so when you go from C1 to C2x, are you adding an x because it's a power higher?
No, I'm adding an x because I have it repeated. So here I have C1 e to the 0 x, right? And then I'll have cx e to the 0 x. Since this is repeated, I need to add an x for each time it's repeated.
Oh, okay.
That makes sense?
Yep, thank you.
Yeah. Now, I want you to ask questions on this one. It's like, ask the questions that you have that you're not saying out loud, because after you teach it like 405 times, like, oh yeah, this is obvious. Like, no, remember you at one point it wasn't. So any other questions on how I produced any of the first two solutions? This one's a lot more straightforward. This one probably did out some. All right, so let's do an initial value problem, and we'll actually end on this one. I'll have something to teach you next time. So let's do this. So here we have this mess. And so step one, we write out our characteristic equation. So it'd be lambda cubed minus lambda squared plus 100 lambda minus 100. I said lambda. It's the second time ever. Right? Either. All right, so we have this. So how do we solve this one? Well, it's the same thing we did before, right? We pull it out, we factor, and we solve. And so here we just go ahead and do this. So step two, what do we get here? So our answers here are going to be lambda is equal to plus or minus plus or minus 10i. This is also factored by grouping and 1. So if I factor by grouping, I get lambda minus 1, lambda squared minus 1. I pull that out, and then so we're going to have lambda squared plus 100. Well, lambda squared plus 100, and we move it over the other side, take the square root, you're going to get plus or minus 10i. Okay. So that's how you do it by head. You can type in a calculator, do the same thing. So once I have this, what are my solutions? So step 3, we're going to write out our general solution. So in this case, we use lambda y equals c1 e to the x. I'm just going to put that one first, plus c2 e to the nothing. So it's e to the 0 power. So it's just going to be cosine of 10x plus c2 sine of 10x. Because here I have no real part, so there is no e part here, since there's no real part. Okay, and this is my general solution. Now what do we need to do? Now we're going to do step 4. So this one actually has the step 4 is use the initial conditions to solve the solve the initial value problem. And so here we're going to use these initial conditions. And let me do it over here. It's just so I have room. So here we're going to have y. And so here we're going to have y of 0. So if I plug in 0 for x here, I'm going to get c1 times 1. I'm going to get cosine of 0 is c2. And then sine of 0 is nothing, right? So sine of 0 is nothing. So c1 plus c2 is equal to 4. Y prime of 0. So here, hi, crunchy computer. So here, I'll take this derivative. This derivative doesn't change at all, so I still get a c1 here. Here, I'm going to pull out a 10, and so we 10 cosine. Well, that's going to end up being 0. And then here I pull out a 10, so this will be 10 sine, or this is 10 sine after I take a derivative. This is 10 cosine. So this is plus 10 C3, which is equal to 11. Here we'll do the second derivative. Here C1 stays the same. This doesn't change, and so this becomes minus 10 cosine, or minus 100 at this point, right? So this would be minus 100 cosine. And then this returns the sign, so it goes to 0. So this ends up being minus 299. Okay. So here we have 3 equations for unknowns. We chunk it through. Even though it looks absolutely insane, the answer is actually quite a benign. There's the answer. And so we write down our hold on, my brain has 2 things in my head. Our particular solution, right? General solution, particular solution. But I used the same vernacular twice. Have I used the same vernacular twice the whole time, guys? Have I said use a particular solution is what happens when we solve for initial values system, and then one particular solution is when we solve for the non-homogeneous case? Have I used that twice? Have I used the same vernacular twice? I might have. I'll think about it. Don't worry about it. So this is e to the x times 1 plus 3 cosine of 10x plus sine of 10x. Okay, and that's the end of this. Any questions about any of this?